Hi everyone. So this morning I'm going to talk to you about high resolution regional weather and climate modelling work that we're doing at the Bureau of Meteorology. And I'd just like to acknowledge all of the input from the Bureau's high-res atmospheric modellers for this presentation. So when we run the model at high resolution, it's computationally really expensive. So why do we do this? And it's really because we see lots of benefits when we push the model to higher kilometre scale resolution. And those benefits come about really due to three main things. So the first is the explicit representation of convection. So we can turn off the deep convection scheme when we're running at the kilometre scales, and that results in an improved diurnal cycle, more realistic rain rates. We see coastal convection propagating more realistically inland. The model's able to represent convective organisation, outflows, backbuilding, better TCs, and the extreme wind gusts associated with convection. We also see benefits because we are better representing the local topography, and you can see the impact of that on the figures down the right-hand panel there that show how the topography changes with increasing resolution. So that gives us better representation of orographic precipitation, land sea breezes, elevated heating, valley cooling, and localised fog. The last benefit comes through having a more accurate representation of the urban areas. So we see better representation of urban temperature distributions, winds, and that has impacts on the air quality forecasts. So if you could move to the next slide. Okay, so we're developing a lot of regional high resolution atmospheric modelling systems. So in this presentation, I'm just going to briefly introduce you to each of these systems. So this is sort of a summary of all of them. So we've developed a pan-Australia 1.5 kilometre scale modelling system, and that's really to advance regional hazard forecasting capability, weather timescales. We're developing urban scale models. So these are models between 1 and 300 metre resolution to support the prediction of warnings on neighbourhood scales. We're developing kilometre scale model for the Antarctic region to best support Australia's interests in the region. We also have developed kilometre scale climate projections and reanalysis model system to advance our regional hazard forecasting capability on climate timescales. Along with all of the model development work, we also work closely with the Met Office to develop and test improved model configurations that underpin our regional weather and climate modelling research that we do in Australia. The last point I'm going to just briefly introduce you to is some of the work that we're just starting now to develop regional coupled modelling system. And so this is to develop prediction systems for multi-hazard compound events, but also these coupled systems will be our future weather and climate systems. Could move to the next slide, please. Okay, so firstly, this is our Pan-Australia 1.5 kilometre weather prediction system that we're calling ACCESS-A. And this system will replace the current city systems that the Bureau runs, which are shown, we have 7 different domains shown in that figure there. So the model's set up with a variable resolution grid where the inner fixed domain is 1.5 kilometres and we have 90 vertical levels. So this is a really big model over 1 billion grid points. We're using the Unified Model Regional Atmosphere and Land configuration called RAL 3.2. This has more complex moist physics in the model, so we do see much improved cloud and precipitation with the RAL 3.2 configuration. We've also spent quite a bit of time updating the land use in the model, which includes improved urban fractions. So as well as this system being able to provide forecast information for the whole country, we're also expecting that because we have such a large domain that we may get some benefits from some scale interactions. So because the tropical convection is represented explicitly, the upscale influence of that on the weather in the tropics and the mid-tropics, and the extratropics may produce more skillful forecasts of things like local extreme precipitation. And there's lots of interesting research that we're going to be doing in that space. So this model is currently with our DA teams who are implementing hourly cycling for DIVA and also blending large-scale information from the global analysis into the model. So that will produce the most accurate initial conditions for this modelling system. So we can move on to the next slide, please. Okay, so we've just started developing the ensemble system that will go be a companion model for ACCESS-A. So this is ACCESS-AE. It's a 2.2 kilometre resolution ensemble system, and it will start off with having 12 ensemble members. So the perturbations for this system come from the global ensemble, so that provides the initial conditions and the boundary conditions. But we also have perturbations coming from some physics parameter. So these are some of the uncertain physics parameters in the model that we perturb to give us some extra spread in our high-res ensemble. So I believe this is going to be the largest convective scale ensemble modelling system that the UM has ever anyone's ever run with the UM, I should say. So there's a really important question that we're going to be looking at here, and that's really how can large domain convective scale modelling improve ensemble systems to better capture extremes. Next slide, thanks. So another convective scale system that we've developed is Barra's C2. So this is the convective scale reanalysis for the Australian Climate Service. This modelling system will support the validation and calibration of climate projections, the development of detailed climatology of hazards, and provide historical contextualisation of extreme events. So Barra C2 is 4.4 kilometres in resolution. It's forced by Barra R2, which is an 11 kilometre system, which is nested in ERA 5. It uses the same RER 3.2 science configuration that ACCESS-A uses, and also has these updated land use, including improved urban fractions. So if you look at the figures on the bottom, if we start with the one on the lower right, this is looking at the precipitation distribution from various models and observations. And you can see that there's one outlier in the curve there, and that's that reddy coloured curve. And that's the Barra R2 system. The other curves are from Barra C2 and observations. So we can see that when we're running the model at the kilometre scale, we get a much better representation, particularly of the heavy rain rates over Barra R2. The C2 system is also able to better capture the wind gusts associated with extreme events, and that's captured in that lower figure there on the left. So that's the maximum wind for this tornado outbreak case that happened in South Australia in 2016. And you can see that the blue line there captures much more intense wind gusts than either Barra R2 or ERA 5, which is a much better representation compared to the observations. So the roadmap for Barra C2, so Barra R2 has completed, is now being updated forward in time, and C2 is ready to start production, with that expected to be complete by mid-2024. Next slide. So now we're looking at BARPA-C, which is the ensemble kilometre scale climate projections for ACS. So by explicitly representing convection, we're expecting to see a better representation of many hazards, for example, TCs, extreme rain and wind gusts. So ACS is complementing the downscale order 10 kilometre projections with a small set of these convection permitting projections. So this again is 4.4 kilometre resolution system that's forced by BARPA-R, which is 17 kilometres, which is nested in various CMIC6 GCMs. And again, using the same science configuration and land use as ACCESS-A. So you can see at the top left, the domains. So the black line is the BARPA-R, the really big domain. Then we have the Cordex domain in red, and then blue is the BARPA-C domain. And just some validation. So on the lower right, we're looking at the minimum sea level pressure and the maximum wind speed for tropical cyclones. So we've got the observations in black, BARPA-R at 17 kilometres in red, and BARPA-C at 4 kilometres in blue. And we can see that BARPA-C, being a higher resolution model, is much better able to represent the observed pressure wind speed relationship for TCs, as we would expect. And then just looking at the rainfall, this is a daily rainfall Perkins skill score. Blue is BARPA-C, red is BARPA-R, and higher is better. So we're seeing improvements in the daily rainfall from the higher resolution run. So just finishing off a one-year trial assessment of BARPA-C, and then for the end of the year, we'll be assessing a 10-year ERA 5 trial assessment. And then for next year, we'll be finalising the GCM selection and downscaling lots of production runs, totaling about 200 years across multiple ensemble members. And the aim is to have that completed by the end of next year. Next slide, thanks. So to support our prediction of high impact weather and to provide more localised information, we're developing urban scale models. So these are models at resolutions of between 1 and 300 metres. So we're developing models for priority Australian domains and also participating in the Paris Olympics Research Demonstration Project. So this is a project that many modelling centres around the world are participating in, and it's really to focus our efforts on developing our future weather forecasting systems at 100 metre resolution. So you can see the model domain there, and this is some results for a heatwave case from July last year. So the top right plot shows the error in the simulated screen level temperatures. And so those green colours are showing a really good result for the model. So in general, we're seeing that the UM is able to produce the urban temperature distribution quite accurately. The red and purple dots there are actually issues with the observations as opposed to the model. And because this is a project involving many modelling centres, we get to compare all of our models to the observations. So the plot down the bottom there is the diurnal cycle of the screen level temperature for many different models and for the observations. So there's two different sites in here. So we've got the black solid line and the black dashed line. And the results for the UM are in that yellowy gold colour. And you can see that the model, that the UM compared to most of the other models is actually doing a really good job at capturing the urban temperature distribution for this heatwave case, which is really encouraging. Next slide, thanks. So we're also developing urban scale models for Australian domains. We've set up a model for the Greater Sydney region. So this is a 333 metre model. It's 1,000 by 1,000 grid points in the horizontal by 90 vertical levels. A lot of work has been done to develop a really detailed urban surface description. And we're using, again, RAL 3.2, and we use the Marusis urban surface scheme. So this is the Met Office of Reading Urban Surface Exchange scheme. So the plot on the lower left there is showing what different globally available data sets look like when you're trying to represent the urban fraction for the Sydney region. And so what we've found is that many of those globally available data sets actually overestimate the urban fraction for Australian cities. But there's a new data set called World Cover that's available. And when we benchmark that against this Geoscape, which is a very high resolution data set available for Sydney, we see that it does a pretty good job of representing the Sydney urban fractions. So that's the data set that we've used to develop our urban model, and is also the data set that we've used to develop our urban fractions for our big ACCESS-A and Barra and BARPA system. Next slide, thanks. Just briefly on our regional high latitude modelling. So we've developed a 1.5 kilometre model over the Davis and Mawson region. So these are 1,500 by 1,500 grid point models. We have really high resolution in the vertical, particularly in the boundary layer with 16 levels below 1 kilometre. And this is using a rotated lat long grid. We also set this up using really high resolution topography, which is really important when you're doing modelling over the Antarctic region. So the work that we've done has demonstrated that there really is value in running these high resolution kilometre scale models compared to the global model, particularly for the wind speeds. So the plot on the left is looking at the wind speed for Mawson. So we have the high res model in blue, the global model in red, and the observations in black. And you can see that the high resolution model is much better able to capture the changes and the magnitudes of the wind speeds. We've also shown that the cloud cover in this new RAL 3.2 configuration does a much better job of representing cloud cover in the Antarctic region, which was underestimated in our earlier version called RAL 2M. So that's the red colours there in the plot on the right. Next slide. Thanks. So the last thing I wanted to talk about is some new work that we're just starting to develop our regional coupled model. And this is following work that the Met Office have done, which I'm showing you on this slide. So they're actually now developing an ensemble prediction system for their regional coupled model to predict multi-hazard compound events up the coast. But we're also expecting to get benefits in coupling, of course, due to the better representation of tropical convection when we couple the atmosphere and the ocean model. So this is an example of a severe storm over the UK, and you can see all of these different models, the atmosphere and the ocean and the wave models all coupled together, producing really good forecasts actually for this coastal flooding event in the UK. So we're just starting to set this model up for a subset of the Australian domain to have a first stab at this. Next slide, thanks. So just in summary, we're developing regional high-resolution modelling systems using this RAL 3.2 configuration for the Australian national domain for kilometre scale weather, climate and reanalysis. We're developing large urban and peri-urban domains for our urban scale modelling systems. we have set up a 100-metre model over Paris, and that's in collaboration with the Met Office to support the forecasting for the Paris 2024 Olympics Research Demonstration Project. We've got a kilometre scale Antarctic model, and in the future, we're going to be developing these kilometre scale coupled models, initially for weather forecasting, but we expect that they'll be the systems that really underpin our future climate and reanalysis models as well. And I lastly just want to comment on that we do work closely with the Met Office to test and improve model configurations that underpin our regional Australian weather and climate prediction work at the Bureau. And I'll finish there. Thanks very much.